Everyone, welcome back, and today let's solve Leetcode problem 1475 titled Final Prices with a Special Discount in a Shop. So I just wanted to quickly apologize for not being too proactive with my posts for the couple of weeks. I've just been getting a little bit busy, and so I haven't been able to consistently upload, but I'll try to be a little bit more consistent for the next couple of weeks and try to manage like 2 or 3 videos daily about the daily Leetcode challenge problems and for my calculus lessons as well. So anyways, let's go ahead and dive straight into the problem here. So we're given an integer array prices, where prices at index I is the price of the ith item in a shop. And there's a special discount for items in the shop. If we buy the ith item, we'll receive a discount equivalent to prices at j, where j is the minimum index such that j is still greater than I, but prices at j is less than or equal to prices at I. Otherwise, we won't receive any discount at all. So basically a 0 discount. So we need to return an integer array answer, where answer at index I is the final price we'll pay for the ith item of the shop, considering the special discount. So as you can see in example 1, we have our input array prices to be 84623, and our output is 42423. The reason why is because for the item 0 or index 0 in our prices array that's equal to 8, we can actually receive a discount from prices at 1, because this index j is greater than this index I, and its value is less than or equal to 8, because of course 4 is less than or equal to 8. And so the discounted price for that index is going to be 8 minus 4, which in other words is simply equal to this 4 for this 0th index or item. And applying that same logic to the other elements, right, basically finding elements to the right of it that have a smaller value, right, the first element that appears like that, or the minimum index that appears like that, is effectively what that's saying. Our final output array is going to be 42423. For the next example here, we see our example 2, our price is equal to 12345, and of course our output is also equal to 12345. But why is that? Well, as you can see, since this is actually sorted in ascending order, every single index for all the elements to the right of it, they're all going to be greater than it. None of them are going to be less than or equal to it, because again, this is in non-decreasing order. And so for that reason, we're not going to get any discount for any of the indices or for any of the items. And so all of them are going to remain unchanged as their original regular price of 12345. We're not going to receive any discount for any of the items. And finally, for example 3, we see our price is equal to 10116, and in this case we output 9016, because of course for the 0th index or item, well, the initial element that has a value that's less than or equal to this 10, that's after it, to the right of it, that's going to be 1. So 10 minus 1 is 9 for the 0th item. And then for this one appears right next to it. 1 minus 1 is 0. And so on and so forth for the rest of the elements, right? For this one, of course, we don't have any discounts because all the elements to the right of it, in this case, it's just a 6, has a value that's greater than this one. And so it remains unchanged. And of course, the same logic applies to this 6 as well. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to solve this problem efficiently, we're actually going to be using a stack data structure. But what exactly is a stack data structure? I'm actually going to comment this out as well. So a stack, right, and before I actually comment it, I'm just actually going to explain what exactly it is and how it actually works in this problem. So a stack is basically, again, a data structure, and the way it works is in a LIFO order. That's also known, or it stands for, in other words, as a last in, first out order. What does that mean? Well, that basically means that the last element or item that we actually add to the stack is going to be the first one we remove. Think about it like a stack of plates. If we have some stack of plates, I'm just going to call it P for short, P, 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 P. Notice how this P was the last element that we actually added. put on the stack, because of course we start with the plate on the bottom, then we add another plate onto it, then we add another plate onto that, and so on and so forth. And this last plate that we added to the top of the stack is going to be the first plate that we pop off from the stack, right? That we remove from the stack. Obviously, we're not going to remove the first initial plate at the bottom first, because that would just simply make no sense. All the other plates would fall right after that. We'd remove this plate at the top, right? That's basically how a stack works, and how the LIFO order is actually gotten from that, right? And why is it actually useful for this problem? Well, stacks are generally very useful, especially for problems when we actually involve comparisons between elements in a sequence. That's also something good to know for general data structures and algorithms for problems like on Leetcode in general, right? But anyways, how is the algorithm going to work for this solution specifically? Well, first we're just going to initialize our empty stack, and this is going to help us keep track of indices of prices from our input array prices. Once we do that, as we actually iterate over our prices array, for each price, we're going to basically have, you can say, a conditional, right? We have to basically check, well, is the current price, is it less than or equal to the price at the index stored at the top of the stack, right? And if that's true, if it actually is less than or equal to the price at the top of the index of the stack, then we can actually calculate the discount for that price at that index and update that in the array. However, if it's not, well, we simply have to just add that index to the current price of the stack and move on to the next iteration. So with that out of the way, let's go ahead and dive straight into the problem here. So I actually forgot to define what a stack was. Let me just do that real quick. Data structure, as you probably already know, in LIFO order, right? And let me actually also comment out that it's very useful for problems involving comparisons between elements in a sequence. And look, I think I probably completely messed up the spelling for most of these words here. There should be elements, not elements. Okay, anyways, now let's go ahead and dive straight into the code here. So first of all, let's actually initialize our empty stack here. So I'm literally just going to call it stack, because that's not actually a keyword in Python here. So stack is equal to an empty stack, right? And again, this is simply going to be used to actually keep track and store the indices of the prices as we actually process them in our input array prices. So once we've actually initialized our stack, now let's actually start iterating over all the different elements, and rather more specifically indices in our input array prices. So for I in the range in Python of the length of our prices, right? And the way we do this is basically getting the index of all the different elements in our prices, right? While the stack is non-null, so while we actually have elements to pop off and check from the stack, right? So we don't have an index out of range. While it's actually non-null, we actually have elements in the stack, and prices at the top index of the stack, so stack at -1 in Python, while that's actually greater than or equal to prices at the current index I. Well, what do we actually have to check here? What is this really doing? Well, basically, the price at the index of the top of the stack, which we can get from stack at -1, at the index of prices, well, if that's actually greater than or equal to the current price, right, which is simply just prices at index I, if that's the case, well, that means we've actually found a discount for the price at the top of the stack. And if we've actually found a discount for that price, well, we can actually set prices at stack.pop. The index basically is popping the topmost index that we're comparing from the stack and setting it equal to that index in our prices array and subtracting it, well, from prices at I, right? This is basically like the discounted computation as the problem defines it to be, right? Basically, again, inside of this while loop here, and I completely forgot the colon here. This should be indented, sorry about that. Inside of this while loop here, basically, we're popping the index from the top of the stack, right, using the stack.pop method in Python, and we actually then subtract the current price, so prices at that index I, from the price at that index. And then we just simply update the prices array at that index after actually subtracting prices at I from its original amount. And once we've actually done that, then for every iteration in this for loop here, in the range of the length of our input array prices, we want to add to our stack, so stack.append in Python, the actual index I, right? So basically, after processing all these discounts for all the applicable items or indices, then we simply have to add the current index I to the stack for each iteration. And that basically means, well, we can actually check this price for future discounts in future iterations, right? And effectively, outside of this for loop here, once this is actually done executing for all elements or indices I or items in our input array prices, and we're done with all these computations, we can simply just return our final prices. Once we're actually done editing it, as you can see on line 8, using our stacks LIFO order, right? So unless I made any syntax errors here, this should be accepted and this should be a valid solution. And as you can see, this is actually just about as efficient as you can get. So, for a quick high-level rundown or reiteration of how this code actually works, first of all, after we actually initialize this stack, basically in this for loop here, for each price, we're basically checking if it can actually serve as a discount for any of the prices that we've already seen, right? And we can check all the prices that we've already seen because they're actually being tracked by their indices in our stack, right? And if it can actually apply as a discount, well, let's actually apply this the discount, right? So we then apply the discount and remove that index from the stack. We pop off that index from the stack, from the top of the stack, right? However, if it can't, well, then simply we just have to add the current index to the stack. And at the end, the prices array is going to finally be updated to contain the final prices after we actually apply all the possible discounts using that stack. So for the time complexity, this is going to be a big O of n solution for runtime complexity, where n is simply going to be the length of our input array prices or the number of items we have. Why is that? Well, because this is really just a one-pass solution. Each index is really just popped and pushed to the stack at most once in this one singular for loop we have to traverse our input array once. And for the memory or space complexity, it's also going to be big O of n, because worst case, in this stack, we may as well, or there's a chance, we store all of the indices in our stack if we don't actually apply any discounts, right? That's the extra data structure that we're using, the extra auxiliary memory, to actually get that big O of n linear time memory complexity as well. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.